Hey, welcome back. In my last video, we took the idea of limits and we broke them down into left and right-hand limits, and we talked about how to find vertical asymptotes. Today, in topic 4, what we're going to do is we're going to use the idea of a limit to define continuity. Now, we already have sort of a basic idea of what continuity is. We know a graph is continuous if you can draw it without picking up your pencil. But using calculus, we can define it in a new way. Okay, if you look here, I've got basically a 3-step process for deciding if a function is continuous at any given point. In order to be continuous, these 3 things have to be true. The function has to exist, the limit has to exist, and those 2 values have to be equal. So using these 3 rules as our new criteria, we can decide if any function is continuous at any point. Before we move on, I want to talk about the ways in which a function is not continuous. So in example 1, what if a function has a spot where the limit exists but the function doesn't? Well, that might look something like this, where you have a graph with a hole in it. Okay? And remember, a hole is also called a removable discontinuity. In example 2, we're asking ourselves, can we draw a function that exists at a certain point but the limit doesn't exist there? The easiest way to draw something like this would be like a piecewise function. Imagine that you've got 2 pieces. Is it true that the function value exists? Yeah, I can see right here I've got a closed circle. So the function exists at this x value, but the limit does not. This is called a jump discontinuity. And finally, in example 3, draw a function where the function exists, the limit exists, but those things are not equal. So imagine a function that has a hole where the function value is misplaced, kind of like this. So we can see at this x value, we'll call it c, f of c exists. I do have a closed dot. The limit exists at c, but they're not equal to each other, so it's not continuous at this point. So you may have noticed in all 3 of those examples, those functions could be expressed as piecewise functions. And piecewise functions are really popular ones to ask questions about continuity. So when we look at example 4, we're asked, is this function continuous at x equals 4? And you'll notice x equals 4 is the breaking point of this piecewise function. So let's talk about it in basic terms, and then we'll come back and revisit it with the calculus definition of continuity. So when I look at this piecewise function, what I want to do is plug 4 into both of these pieces and see if I get the same value. So for x values less than 4, x squared, 4 squared is 16. And for x values greater than or equal to 4, 2x plus 12, 2 times 4 plus 12, 8 plus 12, is 20. Now, because these aren't equal, we have a pretty good idea that this is not continuous. But how do I justify that using calculus? Well, what are my 3 rules? Does the function exist? Yeah, it does. I can see I've got an or equal to right here. Does the limit exist? That's where this falls apart. Because when I plugged 4 into x squared, what was I doing? I was actually finding the left-hand limit. So the limit as x approaches 4 from the left of x squared equals 16, whereas the limit as x approaches 4 from the right of 2x plus 12 equals 20. Because the limit from the left and the limit from the right don't equal each other, the limit does not exist. And so this is not continuous because the limit does not exist at 4. Example 5 is really similar. Is this function continuous at x equals 2? Again, I noticed that 2 is the breaking point. So let's go through the 3-step process. Does g of 2 exist? Yeah, it does. I can see right here, g of 2 equals 3. Does the limit as x approaches 2 exist? Well, I can see that for values of x less than 2, I can calculate the limit as x approaches 2 from the left by plugging into x plus 1. That gives me 3. And I can find the limit as x approaches 2 from the right by plugging into x squared minus 1, which is also 3. So the limit exists, it equals 3. The function exists, it equals 3. Because those are the same, this is continuous at x equals 2. In example 6, I'm asked to find all values of x where h of x is not continuous. So the first thing I want to do is just look at these 3 pieces one by one. X squared minus 1 is a quadratic function. It's continuous everywhere. The square root of x plus 1 is continuous for all values of x greater than or equal to -1. And when I look at this domain right here, I can see it runs from -1 to e, so we're good there. Natural log of x is continuous for all values of x greater than 0. And again, when I look at this domain, I see we're using natural log x for values of x greater than e, so again, we're good there. So now the question becomes, if all 3 pieces are continuous, are they continuous at the breaking points? In other words, at -1 and at E, is the graph coming together, or is it not? So to answer that question, we're going to consider left and right-hand limits, starting at -1. So the limit as x approaches -1 from the left of x squared minus 1 would be 1 minus 1 is 0. The limit as x approaches -1 from the right of the square root of x plus 1 is also 0. So the limit exists at 0, the function exists at 0. Both are 0, so it's continuous at -1. What about at e? The limit as x approaches e from the left of the square root of x plus 1 is going to be the square root of e plus 1. And from the right, the limit as x approaches e from the right of natural log x is going to be natural log of e, which is 1. Okay? These are not equal, so the limit does not exist at e, therefore h of x is not continuous at e. All right, we're going to shift gears now and talk about the intermediate value theorem, or the IVT. Now, the idea behind the intermediate value theorem is pretty simple. First of all, you have to have a continuous function. You take a continuous function, you pick any 2 points on that function, and the intermediate value theorem guarantees that the function will attain every y value between the first one and the second one at least once. It's impossible to draw a continuous function that doesn't satisfy the intermediate value theorem. Now, is it possible that the function attains values outside of that range? Sure, it could look like this. But still, the fact remains, every value between those two has to be hit by the function at least once. Maybe more, but at least once. All right, so with that in mind, let's look at example 7. Consider an unknown continuous function that satisfies f of 1 equals 4 and f of 6 equals -3. So I immediately notice 2 things here. First of all, they tell us that it is continuous, which I need to know that it's continuous to use the intermediate value theorem. And as x goes from 1 to 6, the function goes from 4 to -3. And so I'm asked, does the function f of x have any roots? Well, if it moves from 4 down to -3, it has to cross the x-axis at least once. And because it's continuous, I can use the intermediate value theorem to make that claim. So next we're asked, does the function equal 2 anywhere on the interval from 1 to 6? Well, again, from 1 to 6, the function travels from 4 down to -3. So it must hit 2 somewhere. And I can use the IVT, again, because it's continuous. I can't stress enough how important it is that it is a continuous function. Next up, consider f of x equals -x squared plus 2x plus 3. Does the IVT guarantee that f of x equals 4 somewhere in the interval 0 to 3? Well, because they gave me the interval 0 to 3, I want to know what f of 0 is and what f of 3 is. So f of 0 would be 3, and f of 3 would be -9 plus 6 plus 3 is 0. So from 0 to 3, this graph goes from 3 to 0. So does the intermediate value theorem guarantee that it will hit 4? Well, I know it travels from 3 to 0. So the intermediate value theorem cannot guarantee that this function hits 4 at any point. Now, what's interesting is it does. If you plug in 1 for x, you get -1 plus 2 plus 3 is 4, and 1 is in the interval. So I'm not saying it doesn't happen. I'm saying the intermediate value theorem can't guarantee it happens because the IVT only guarantees that it will hit every y value from 3 down to 0. All right, moving on to our AP problems. 2008 AB number 3 says the function f is defined above. For what value of k, if any, is f continuous at x equals 2? Well, for this piecewise function to be continuous at 2, I want these 2 pieces, x squared minus 3x plus 9 and kx plus 1, to be equal to each other when x is 2. So I'm going to plug in 2 for x, set them equal to each other, and solve for k. So plugging 2 into the top piece gives me 4 minus 6 plus 9 equals, plugging 2 into the bottom piece gives me 2k plus 1. Simplifying that, I've got 7 equals 2k plus 1, 6 equals 2k, so k must equal 3. So my answer is C. 2012 AB number 9, very similar problem. Let f be the function defined above. For what value of k is f continuous at x equals 2? So what's important to point out here is that when you look at this top part right here, notice these canceling factors. So this graph has a hole at 2. The question is, what value do I need to plug that hole with to make it continuous? And so after canceling these out, if I plug a 2 into what's left, 2 times 2 plus 1 is 5. So my answer is E. 2012 AB number 77, ignore answer choices D and E on this one. Let f be a function that's continuous on the closed interval 2 to 4 with f of 2 equals 10 and f of 4 equals 20. Which of the following is guaranteed by the intermediate value theorem? Well, let's point out some things here. They've mentioned the intermediate value theorem. So I want you to think, what has to be true to use the intermediate value theorem? Well, this function has to be continuous, and they took care of us there as well. They said it's continuous, so we're all good there. As this function moves from 2 to 4, it changes from 10 to 20. So any value between 10 and 20 is going to be attained between x equal 2 and x equal 4. And when I look at answer choice A, I see f of x equals 13 has at least one solution in the open interval 2 to 4. That's exactly it. Between 2 and 4, am I going to hit 13? At least once, because it's between 10 and 20. So A is my answer. And last one for today, 2012 BC number 83. If a function f is continuous at 3, which of the following must be true? Answer choice A, f of 3 is less than the limit as x approaches 3. That's not right. If it's continuous, then those have to be equal to each other, so that's out. Answer choice B, the limit from the left doesn't equal the limit from the right. Well, if it's continuous, the limit must exist, which would mean the left and right-hand limits would have to be equal to each other. And C, f of 3 equals the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. There we go. In order to be continuous, the function has to exist, the limit has to exist, and they have to be equal. So C is our answer. All right, so to recap, we say a function is continuous at a point if the function exists at that point, if the limit exists at that point, and if those two values are the same. Also, the intermediate value theorem says that if a function is continuous between 2 points A and B, then it will attain every value between f of A and f of B at least once. Hope that helps. Thanks for watching.